One very useful equation that allows you to calculate the quantity of a gas given its pressure, volume, and temperature is the universal gas law. To solve problems using the universal gas law, you do need the universal gas law constant. I've given it to you in two values, 0.0821, and this is in liter atmospheres per mole Kelvin. And then also we have an R value of 8.31 liter kilopascals per mole Kelvin. The only difference between the two is whether you're talking about using pressure in atmospheres or pressure in kilopascals. Kilopascals is the System International unit, where atmospheres is one that is used here in the States most often. So we're going to be using both, probably more the 0.0821 in the example problems that we'll be looking at today. Bottom line is there are 4 units attached to R, so you've got to be careful with units. So if we're using 0.0821, your volume has got to be changed to liters. Your pressure has got to be in atmospheres. Temperature has always got to be in Kelvin. And if the quantity of gas you're dealing with is not in moles, you're going to have to change it to moles. So let's see if we can solve a problem using the ideal gas law. In this example, we'd like to know what volume a gas would occupy if they give us that we have 48 grams of methane at a certain temperature and pressure. So here we're going to get to highlight how you can calculate the volume of a gas if you know the quantity of that gas. Once again, we really do need to be paying attention to units. So what we're going to see here is that we're going to need to change the mass of our methane, the CH4. We're going to need to change that to moles. So we need to add up a molar mass. If we visit our periodic table, we see that carbon has an atomic mass of 12 and each hydrogen has an atomic mass of 1, and that adds up to be our 16 grams per mole. So if you take the mass, the 48 grams, and divide it by the molar mass of methane, that's how we obtain an N value, our quantity of gas, of being 3 moles. To be able to solve for that volume, we've got to make sure that our temperature is in Kelvin. It was provided in Celsius, so to change Celsius to Kelvin, you simply add 273. And then if we're going to use 0.0821 liter atmospheres per mole Kelvin, the pressure that's provided has got to be in atmospheres. Here it was in torr, 1280, and to change torr to atmospheres, all you have to do is divide by 760. So 1280 divided by 760 is how we obtain the 1.68 atmospheres. So if you take your ideal gas law, PV equals nRT, and algebraically rearrange to solve for volume, you'd have what we see in front of us, that volume is equal to nRT divided by P. So if you plug in all the values up above, plug in your moles, the universal gas law constant, our temperature in Kelvin, and our pressure in atmospheres, we'll be able to calculate the volume of methane at the conditions stated. And in this case, this is going to be 61 liters. We're now going to use the ideal gas law to calculate the volume of a gas, CO2 in this case, that can be produced at non-standard conditions, starting with the reaction of 300 grams of calcium carbonate with excess hydrochloric acid. So if we can get the moles of CO2, we're going to be able to use our ideal gas law to solve for the volume. So the first thing we got to do is some basic stoichiometry. We've got to take the 300 grams of calcium carbonate and see what quantity of CO2 we're going to be able to produce. So the first thing we need to do is add up a molar mass for the calcium carbonate. If we visit our periodic table, we're going to see that calcium is worth 40 grams per mole, carbon is worth 12, and each of the 3 oxygens is worth 16. If you add up that molar mass, that is the 100. So to change grams to moles, you have to divide by the molar mass. The ratio between the calcium carbonate and the CO2 in the balanced equation, it is a 1-to-1 ratio. For every 1 mole of calcium carbonate that we start with, we're able to produce 1 mole of the carbon dioxide. So the quantity of gas that we're able to produce here, the amount of CO2, is 3 moles. So within the ideal gas law, PV equals nRT, we now have our N value. So if we'd like to know what volume of CO2 can be produced, let's use that 3 moles. And let's plug it into our gas law. Let's rearrange to solve for volume. And volume here would be equal to the moles, N, times our universal gas law constant, R, and our temperature in Kelvin, all divided by the pressure in atm. So if we plug in that we have the quantity of the gas is 3 moles, plug in our R value, the 0.0821 liter atmospheres per mole Kelvin, our temperature in Kelvin 300, and our pressure in atmospheres, we're going to be able to figure out that starting with 300 grams of calcium carbonate that we're able to produce right at 148 liters of the carbon dioxide. So the ideal gas law allows you to calculate the volume at non-standard conditions. If we had STP, we could have used 22.4 because 1 mole of any gas at STP conditions does have a volume of 22.4 liters. But in this case, we had non-STP conditions. We had half of an atmosphere pressure and 300 Kelvin, so the ideal gas law allowed us to calculate the volume knowing the moles of gas that had been produced.